So section 3 is our remaining section. And in this section, we're actually going to look at how to utilize or how to harness the electron flow that's occurring during redox reactions. So we're going to know terms such as voltaic cell, the anode, cathode, cell potential, and salt bridge. And we're going to be able to say what happens during these reactions when we put them into these cells. We'll also be able to describe the voltaic cell, the different parts, what each component is made of, and we'll understand the direction of flow of electrons in each of the components of the voltaic. So for voltaic cells, we're going to actually utilize the separation of our oxidation and reduction reactions in order to facilitate actually harnessing the electrical energy that exists within redox reactions. And so instead of keeping our reactions in the same container, like we've seen where the copper is being deposited upon the zinc electrode, what we're actually going to do is we're going to separate them into two locations. So we have our anode side and our cathode side. And what you need to understand there is that electrons are going to move from the anode to the cathode. And you're going to have your two different reactions in two different locations. And we're going to look at very specific examples of this. And the other things that you need to, I guess, keep in the back of your head is that we're using reactions that are going to occur on their own anyway. So these spontaneous reactions are what we're utilizing to emphasize, or not emphasize, but to harness or utilize this electrical flow. And this electrical flow that we're harnessing obviously gives us some ability to actually harness electricity. So this is a voltaic cell. And what you need to understand is that it converts chemical energy into electrical energy. And the other thing that you need to mark or keep in your head is that electrons always flow from the anode to the cathode. Okay, so anodes, guys, down here are our definitions, is where the oxidation occurs. Okay, so that's where electrons originate from. Because remember, something that's being oxidized has become more positive. So it's got rid of its electrons. Those electrons are going to flow through this external circuit all the way to the cathode. And those electrons are going to do the reduction. So what you need to understand is this left-hand side, okay, where this oxidation is occurring, where this anode is, the solution is going to be becoming more positive because we're going to be putting positive ions into solution. And the right-hand side, we're going to be reducing, okay. So we're going to be either pulling positively charged ions out of solution, okay, or we're going to be basically making that solution more negative, okay. So because of the fact that the charges of the solutions at the anode and the cathode are becoming more positive and more negative, we're going to have to counterbalance that buildup of charge. Okay, and we do that because if we don't balance the buildup of charge, okay, the cell is eventually going to die. So what that means is eventually no more electrons are going to flow. Okay, so in order to do that, what we're going to do is have something called a salt bridge. Okay, it can be a salt bridge or a porous disc. So what a salt bridge is a salt bridge actually has ions in it that will flow to the appropriate locations. Okay, so this one is becoming, this anode is becoming more positive. Okay, so negative ions are going to flow that direction. Okay, the cathode is becoming more negative. So positive ions are going to flow this direction. So that would be an example of using a salt bridge. Now sometimes we can also use a porous disc, which allows the negative and positive ions to flow freely between the two cells. So those are the two options to help make sure that our cell doesn't quote-unquote die. Okay, now the electrodes that we're looking at here, guys, these are the electrodes right here, these things that we're sticking into solution. Okay, so electrodes a lot of times are made of metals that are part of the reaction, so like copper or zinc. Okay, but sometimes we have things in reaction that we're not able to make solid bars out of. So In those situations, we'll use platinum or graphite as basically generic stand-ins. Okay, so we have these electrodes. We know what our electrodes are. Okay, so this is our anode cell. This is our cathode cell. Okay, and this is our salt bridge or our porous disk. And these are the pieces of the voltaic cell that you need to be familiar with. So let's go ahead and look at a very specific example. We've already seen this reaction. If we go ahead and take a look down here, okay, we see the oxidation of the zinc and the reduction of the copper and an overall net reaction. Now what we've done in previous sections is we've separated out these oxidation and reduction reactions and balanced them and done various things with them. Okay, so in this situation what we've done is we've written our two half reactions. We know that oxidation occurs at the anode. So what we've done is we've established an appropriate solution to facilitate this oxidation. We've done the same thing on the reduction side, on that cathode side, and we've created a solution that facilitates the appropriate reduction associated with this type of reaction. Okay, and we've seen this before. We've seen this where if we put the copper sulfate solution into a beaker and add a zinc electrode, that we get this buildup of copper on the zinc electrode. Now, instead of putting these together in one pot, we actually want to separate them out so that there's an electrical flow, as we see here. So what's physically happening here is we have this zinc sulfate solution. Okay, we have a zinc anode. Okay, and then over on this side we have a copper sulfate solution and we have a copper electrode. Okay, in this situation, the oxidation and reduction components allow us to utilize zinc and copper as our anode and cathode electrodes. Other examples will have a platinum or a graphite example. It depends on what you have in your solution. Okay, so what's actually happening here is that the zinc atoms in the anode are being oxidized. And what that ends up causing is zinc 2 plus ions to go into solution while releasing electrons up through the anode. So those electrons, they come on up, they flow over to the copper electrode. They flow down into the nicely conducting copper. They come out to the solution, and those electrons reduce the copper 2 plus anion. The copper 2 plus anion then becomes copper 0 and plates or coats the surface of the copper electrode. So what's happening is electrons are flowing from left to right hand side, basically creating a electron flow and potential energy. Now, what we're going to see in solution is we're actually going to see change in concentrations of specific ions. So we talked about this anode side. We talked about those zinc 2 plus ions increasing in solution. Why? Because as oxidation occurs, these zinc 2 plus ions are being generated from the electrode. Okay. In contrast, on the right-hand side in the cathode, okay, we're seeing these copper 2 plus ions being pulled from solution to give us the copper 0 plating on that electrode. So what's actually happening in terms of charge increase or decrease is that on the anode side, we're seeing an increase or a more positive setup in solution, and on the cathode side, we're seeing a more negative increase. So zinc ions are being put into solution, okay, and copper 2 plus ions are being taken out of solution. So overall, we have an increase or a more positive ion concentration, and on the right hand side we have a more negative ion concentration. So what we need to understand there is that our salt bridge is going to come in and actually help counterbalance that. So that's why our potassium ions in this particular salt bridge are going to go ahead and move over and help counterbalance the decrease in positive charge. Okay, our chloride ions are going to come over and help counterbalance the increase in positive charge on the left-hand side. And this is an actual physical, real-life, spontaneous voltaic cell reaction. And as you can see, they work in tandem in order to harness this energy in terms of electrical flow. So how do we describe voltaic cells? Okay, well, we're given a chemical reaction. Okay, we're giving an example right here. Okay, and the first thing we need to do is we need to divide our chemical reactions into half reactions. And we've already been doing this. We know how to do it based on oxidation and reduction, right? We know how to do that, so we've done that. Okay, we're going to balance the half reactions according to the rules. So in this case, it's going to be acidic conditions. And we're going to go ahead and we're going to balance these half reactions. So once we've done the balancing of the half reactions and we know how many electrons and how many hydrogens and oxygens and all that good stuff that we're supposed to have, we're then going to go ahead and describe what's happening on each side. So we know that on the left-hand side we are going to have our oxidation step occurring. So we know that we are going to have a release of electrons. So we know that over here we're going to have various things. So for instance, iodide, we know we need a source for iodide in the solution. So in this case, we're going to have a potassium iodide solution on the left-hand side because that's what we need for our source. The fact that we have a reduction step or a reduction half reaction, we have a chromate anion present. Okay, so we know that we're going to have a potassium chromate solution in order to facilitate this. So once again, we know what's going to be in our anode and our cathode because we know that we need to have our oxidation and our reductions in specific locations. Okay, and if we look at these examples above, neither dichromate nor this iodine are going to give us solid electrodes. So in this case, we know that our electrodes are either going to be made of platinum or graphite. Okay, so we know what goes in our anode cell, we know what goes in our cathode cell. Okay, we know what our electrodes are going to be made out of, and we definitely know that we're going to need a salt bridge of some sort. Okay, so we need a positive and a negative ion source. So, and we want to dictate which direction each of those goes. Okay, so we know that the oxidation solution is going to be becoming more positive on the anode side. Okay, so we're going to need to add negatively charged electrons. Okay, and on the right hand side at the cathode, we're definitely going to be having to add a positive electrode in order to balance out the electrical charge and not end up with a dead cell. So this is how we would describe a voltaic cell. You're going to make sure that you indicate where the oxidation and reduction are occurring, which one's the anode and the cathode, what your electrodes are made out of, and what direction your salt bridge ions are going to flow. And last but not least, you always want to make sure that you're indicating that electrons are flowing from your anode into your cathode. So once again, a reminder about the salt bridge, or that porous disk. We need to make sure that we always add this to our description of the voltaic cell. We mentioned it on the last option, but make sure you're dictating if it's a salt bridge or a porous disk. Make sure that you're familiar with each of them and how they're different from one another, and basically understand why they're important. Okay, we need to make sure that we have them because they're going to make sure that the net charges in each of the solutions remain at 0, so that we don't have a charge buildup and subsequent stopping or a subsequent end to the flow of electrons. Okay, so we need to know what each of them are, how they're different, and why they're important. So the last thing we're going to talk about here for this unit is we're going to talk about cell potential. We'll talk about this in much more detail the next time we revisit this during second semester. But what we need to understand is cell potential is basically the measure or the outcome of the movement of electrons from one cell into the other. Okay, so that driving force, that flow of electron is the cell potential, or sometimes called the electromotive force. Okay, so the unit of electrical potential is measured in volts, and you guys have seen this type of measurement before. And it corresponds to a joule of work per coulomb of charge transferred. And we're going to look at how to do calculations with this later. But just be familiar with the phrase and the wordings, and the wording, because it may come up in terms of, why is cell potential important, or how does cell potential affect the overall energy that you can obtain from a oxidation reduction potential reaction. And as you know, the voltmeters are what we've seen throughout most of the reactions, and they're utilized to measure what the actual cell potential is. Okay? Last thing to remember and to always keep in your head is that electrons always flow from the anode, okay, to the cathode. Okay? Always anode to the cathode. If you're ever in doubt, think about what's happening at the anode, right? Oxidation. When oxidation occurs, electrons are released. Okay, what's happening at the cathode? Reduction. Okay, so electrons are being picked up. If you remember what happens at the anode and what happens at the cathode, you won't have to worry about what is happening in terms of electron flow in a cell. So that sums up Unit 3, or Section 20.3. And at this point, this is what you need to know for this next test. So we'll visit this stuff some more second semester. Good stuff.